Welcome to the deep dive. Today, we're not really just, going through a report.
No.
We are launching what feels like an urgent adventure, a quest, really, in resource conservation.
I like that. A quest.
And we are heading straight into the literal trash.
We are.
Specifically, the shredded, chaotic, just complete mess of metal you find inside a junked car.
And this isn't just about, cleaning up the environment. Our mission here is to really understand this high-stakes kind of alchemy.
Alchemy is the perfect word for it.
It is, right. How do you take that complex, totally impure stream of scrap metal and somehow turn it into the high-tech structural materials that we need for the next generation of cars?
Yeah, how?
Well, we're going to blend some proprietary market research with some pretty groundbreaking metallurgical science to try and find the answer.
We are on the quest for the ultimate green metal. And get this, the energy that is just embedded in a single piece of discarded aluminum. It's like a hidden mountain of treasure.
It really is.
And if we can figure out how to recover it efficiently, the environmental and, honestly, the economic leverage is, well, it's truly unbelievable. So I want you, our listener, to take a little mental field trip with me.
Yep.
Don't think about the sleek car you drive every day. I want you to think about what it took to actually manufacture the primary aluminum that makes up its structure.
The virgin metal.
The virgin metal. It starts with bauxite mining, and this is a massive scale operation. I mean, it dramatically alters the landscape.
Oh, huge scars in the earth.
Then you have to refine the alumina, and then finally you get to this colossal energy brute force of electrolysis.
It really is an industrial marathon. Primary aluminum smelting is a continuous, high-temperature operation that is just spectacularly demanding when it comes to energy.
I mean, we're talking about furnaces that essentially run on massive, constant electrical current.
All day, every day.
Just to split the aluminum oxide and, free the actual metal.
It's a brute force process.
And when you look at the life cycle assessment, or LCA, which is, the industry jargon for tracking the environmental cost of a product from its cradle.
The mine.
Right, the mine, all the way to its gate.
The factory exit.
The numbers are, well, they're genuinely shocking.
They really are. So we look at the data for producing just 1,000 kilograms of primary aluminum.
1 ton.
1 metric ton of the virgin metal from that bauxite ore. That single ton requires an astonishing 186,262 megajoules of energy.
Okay, wait. 186,262 megajoules.
Yep.
That number is huge, but it's totally abstract. We need some context here. How big of an energy footprint is that, really?
That's a fantastic point because the number itself is almost meaningless.
Yeah.
So to give you some perspective, 186,262 megajoules is the energy equivalent of nearly 52,000 kilowatt hours.
52,000.
So in California, for example, that's enough electricity to power an average home for over 4 years.
No way.
For 1 ton of aluminum.
4 years of electricity for one house, for 1 single ton of metal.
Wow, exactly. And, if you compare it to other common materials like steel, the disparity is just enormous.
Right.
Primary aluminum production across the board is generally 8 to 9 times more energy intensive than producing primary steel.
8 to 9 times.
That massive energy investment is just sitting there. It's embedded in every sheet of structural aluminum on the road today. It's the cost of entry for getting that lightweight strength.
Okay, so that's the cost side of the ledger. But this is a deep dive, so let's get to the incredible flip side of this. If you take that same 1,000 kilograms of aluminum, but you source it from collected scrap from a junkyard, what does the energy bill look like then?
This is where it gets crazy.
Yeah.
This is where the environmental and the economic leverage becomes the core driver for the entire recycling market.
Okay.
Making that identical 1,000 kilograms of aluminum, but using scrap metal as your feedstock requires only 11,690 megajoules.
Wait, hold on. Let me just process those two figures.
Yeah.
We go from 186,262 megajoules for virgin metal all the way down to 11,690 for recycled.
It's a collapse.
That's a reduction of what, about 94 to 95%?
Yeah.
That's not just like a sustainability goal. That's a fundamental re-engineering of the entire economic cost structure.
It is. And that 95% energy saving, it translates directly into enormous reductions in manufacturing costs, operational expenses, and of course, greenhouse gas emissions.
Of course.
So for original equipment manufacturers, the OEMs, the big automakers of recycled aluminum, becomes a near zero carbon value input into their manufacturing cycle.
A near zero carbon input.
It helps them meet these tightening regulatory requirements for fleet efficiency and emissions, which are, massive market drivers right now.
So the profit motive and the planet motive are finally perfectly aligned.
They finally shake hands.
Every discarded car suddenly contains this battery pack of embedded energy that we absolutely must recover. It's become a strategic necessity, not just a feel-good measure.
Absolutely. The competition in the automotive sector, it demands it. Automakers are scrambling for ways to cut manufacturing costs, while at the same time, appeasing consumer preference for eco-friendly materials.
That's a huge selling point now.
It's a massive competitive edge.
Yeah.
When you can announce that your new chassis uses aluminum that required 95% less energy to create, the sustainable supply chain is becoming the profitable supply chain.
So that 95% savings sounds like a cheat code for the industry.
It should be.
So why aren't all new cars just made from old cars? It seems so simple. And this is where we meet the villain of our story, the thing that basically poisons the well, contamination.
The problem isn't the aluminum itself. It's the sheer mind-boggling complexity of a modern car.
Right.
When that vehicle reaches its end of life, what the industry calls an ELV, an end-of-life vehicle, and it gets put in a shredder.
Right.
All those highly engineered, very specific aluminum components get homogenized into a single, chaotic, unusable mush.
So we have to understand that not all aluminum in a car is created equal.
Not at all.
There are two primary types, and you're saying they're like oil and water when it comes to high-value recycling. We're talking about wrought alloys and cast alloys.
That's the absolute crux of the issue. Wrought alloys are the high-performance superstars. Think of them as the metal sheets, the frames, the crash structures, the body panels.
The important stuff.
The stuff that has been mechanically worked, so it's been rolled or extruded, to give it super high strength and ductility. They need pristine, highly specific chemistry and an internal structure to function in a structural safety critical capacity.
Okay, so those are the good guys, and then you have the cast alloys.
Cast alloys are bulkier. They're poured into a mold. Historically, they were used for things like engine blocks, transmission casings, wheels. They're much more tolerant of impurities, but they contain concentrations of other elements that are just toxic to the high-performance wrought alloys.
Okay, let's pull out the sports analogy here to really define this incompatibility crisis. Wrought alloys are like your champion marathon runner. They need pure oxygen, precise nutrition, specific training. Their whole performance relies on perfection.
A perfect analogy.
Yeah.
And the cast alloys, while they're strong in their own way, they contain what we call tramp elements.
Tramp elements.
These are the impurities, so copper, iron, zinc, or even just high levels of magnesium that exceed the limits that are required for those structural wrought parts.
So the tramp elements are the bad players you're adding to the team.
Yeah. They're the ones who show up late to practice and eat junk food. If you try to mix these two streams, those tramp elements just ruin the whole team chemistry.
So if you mix that high purity wrought scrap with the cast scrap, what physically happens at the molecular level? What makes the resulting metal so useless for a new structural part?
It's a physical poisoning of the metal. Iron and copper in particular are the disaster elements for these high-performance alloys.
The worst defenders?
By far. They don't integrate nicely into the aluminum's crystal structure. Instead, they rapidly form these tiny, brittle intermetallic compounds.
What does that mean?
Think of them as microscopic, glass-like shards at the grain boundaries of the metal.
Microscopic glass shards embedded in the metal. That sounds really bad for strength.
It's catastrophic. These shards completely destroy the ductility and the tensile strength of the metal.
Yeah.
If you use that contaminated metal in a body panel or a crash structure, it's not going to absorb impact the way it's designed to.
You'll just crack.
It becomes brittle, and it's prone to cracking under stress. That's why the OEM quality standards are so incredibly, incredibly high.
And that contamination phenomenon forces what the industry calls downcycling.
Yep.
So you've taken this perfectly good, high-value, high-energy wrought aluminum, and because of the mix, the only safe thing you can turn it back into is a lower-quality cast alloy.
Exactly.
You've essentially degraded a marathon runner into a heavyweight.
And this is just an incredibly inefficient use of a scarce, energy-rich resource. We are losing value, and we are losing structural potential with every single melt. And this problem, it's accelerating toward a crisis point. A full-blown crisis, driven by the shift to electric vehicles.
Wait, why is downcycling suddenly a crisis now? We've been recycling cars for decades. What changed?
Historically, the internal combustion engine block, was the main reliable destination for all this stuff. We
Ah.
called it the scrap sink. It took all that low-grade mixed aluminum scrap. The engine block material was relatively tolerant of impurities. It was the trash can that could safely absorb all those alloy mistakes.
But the EV revolution is literally removing the trash can.
Exactly. Electric vehicles remove the engine block entirely.
It's just gone.
Gone. Which means the primary destination for all this mixed low-grade casting material just vanishes. And the projections are dire. Some models suggest this change could lead to a massive global surplus,
How massive?
potentially generating 6.1 million metric tons of unrecyclable low-grade scrap by 2030, just because we lost that sink.
6 million tons of useless metal.
That's a monumental liability that the industry has to solve for right now.
And the irony remains that EVs desperately need more of the good stuff, more of the wrought aluminum for lightweighting, to offset the heavy weight of their battery systems.
It's a huge paradox.
So we have demand for high-quality, pure structural metal going up, and the available pool of pure scrap is effectively going down.
The industry is being squeezed from both ends. Passenger vehicles already consume the largest share of aluminum scrap, due to all these lightweighting efforts, but EVs are the future. Solving the downcycling disaster is paramount to securing the supply chain for zero-emission vehicles.
The moment that OEMs and recyclers realize that relying on the old scrap systems, basic magnets and people sorting by hand, was not going to cut it for the high-volume, high-value needs of the EV future. Well, that's when the quest for a technological solution really began. And the goal was simple, but the execution was immensely complex. Separate the toxic rot scrap from the pristine cast scrap with near-perfect accuracy.
And the existing infrastructure, especially in North America, was built for the 20th century. It's aging, and it's just not capable of the efficient, precise segregation that we need now. It demanded a revolutionary investment in technology.
So where's the weak link?
Specifically in the sorting process. That's the bottleneck.
So how do you take a mixed pile of metal fragments, and some of these are as small as a pebble, and tell at an elemental level that this one tiny fragment has too much iron and this one is pure enough to become a car door?
Yeah.
We need the scientific toolkit.
Right, so we have to move beyond simple physical separation to basically chemical fingerprinting. For bulk sorting, we do still use eddy current separators.
What do?
They just separate the non-ferrous metals, like aluminum, from everything else. But to get to the alloy level identification, we need the serious firepower.
Okay.
We're talking X-ray fluorescence, or XRF, and laser-induced breakdown spectroscopy, or LiBS.
Okay, let's unpack that jargon, especially LiBS. Laser-induced breakdown spectroscopy, how does that even work?
Okay, think of it like a rapid-fire chemical sniper. A LiBS machine fires this powerful focused laser pulse at a fragment of metal, and that pulse is so intense that it instantly vaporizes a tiny amount of the metal, creating a superheated plasma plume.
A microscopic explosion on every piece of metal.
Exactly, a tiny little star. And the light spectrum that's emitted by that plasma plume is unique to the elements that are present in the sample.
So it's like a chemical barcode.
It is a chemical barcode. The spectrometer reads that barcode and instantly tells you the exact elemental composition of that piece of scrap. And specifically, it's identifying those pesky tramp elements like copper and iron. It is the absolute state-of-the-art tool for this.
That sounds incredibly accurate, but I'm guessing also incredibly complex and expensive to deploy at massive scale in a scrapyard. Is that the trade-off? High cost for high purity.
That is the trade-off. LiBS is exceptional for accuracy, but it has throughput limitations and operational costs. It's analyzing chemistry faster than you can blink, but you need dozens of them running non-stop to process the millions of tons of scrap generated every year.
Let's use the video game analogy again. The old system was like throwing all your inventory into one big bag.
Yeah, a mess.
Now, LiBS is like equipping a high-end AI scanner that identifies the exact molecular signature, the weakness of every single enemy fragment, but it takes precious milliseconds for every single scan.
Precisely. And to make those scanners even smarter, the industry is now integrating artificial intelligence and machine learning algorithms.
Of course they are.
The machines actually learn the subtle spectral differences between different alloy grades. So, for example, distinguishing a 5XX series alloy from a 6XX series alloy, and they get better over time, improving sorting accuracy and efficiency in real time.
Now let's discuss the truly brilliant innovation that seems to kind of sidestep the LiBS cost problem. You mentioned a chemical treatment method that sounds like giving the scrap a secret code.
This is a perfect example of solving a high-tech problem with a beautifully low-tech answer.
I love those.
So scientists realized they didn't need LiBS for every single piece if they could just pre-identify the material family cheaply. So they developed a chemical treatment to color code scrap aluminum pieces by alloy family. Specifically, those high-value 5XX and 6XXX wrought alloys.
Wait. They chemically stained the aluminum so that different alloy types literally turn different colors.
Essentially, yes. This chemical color coding then allowed for low-cost, high-speed optical sorting.
Optical sort.
Instead of using million-dollar lasers, they could just use advanced cameras and computer vision to identify the color and segregate the material.
That's brilliant. Optical sorting is fast and it's cheap. So if the machine sees a specific color, it knows. That's a high-purity wrought alloy piece. Divert it here.
Exactly.
What was the purity result of this simplified method?
The results were stunning. This process successfully achieved greater than 95% purity in the resulting cast and wrought fractions. You've completely bypassed the most expensive analytical step while achieving a purity level that you need for closed-loop recycling. It creates a circular supply chain where that sorted, high-value wrought sheet scrap can go directly back into new, high-value wrought products, like structural frames.
So that significantly addresses the infrastructure constraint. Once the scrap is sorted, the general process is what? Shredding, then this super advanced sorting, then melting, and finally casting or forming into the new product.
And this quest, it requires total, non-negotiable cooperation across the entire supply chain. This is not a lone recycling company's job.
It can't be.
The OEMs, the big global automakers, they set the quality standards. They need to design cars that are easy to recycle in the first place. Aftermarket participants like scrapyards and shredders, they need to invest in this advanced equipment.
Right.
And the recycling companies have to collaborate closely with the OEMs to ensure traceability and efficient material flow. It's all about creating these integrated, closed-loop ecosystems where the material never leaves that high-value stream.
It sounds less like a quest and more like an entire industrial retooling initiative.
It is. The scale of the challenge and that 95% energy reward demands nothing less.
So we've established that high-tech sorting is crucial, and the low-cost chemical color coding solution is, frankly, brilliant.
It's amazing.
But let's remember our original goal, neutralizing the villain. What if the ultimate solution wasn't just sorting better, but inventing a metal so clever that it fundamentally doesn't need perfect sorting?
That was the true holy grail for materials scientists. To find a metallurgical answer that could take the chaotic mixed scrap with all its inevitable impurities and turn it into something premium right out of the furnace.
And without having to dilute it with expensive virgin metal.
Exactly.
And the research squares delivered, didn't they? They found a process for directly upcycling mixed end-of-life vehicle scrap into a new, high-performance aluminum alloy.
Yes. This new alloy is the answer to the downcycling disaster. It is specifically designed to be compositionally tolerant.
What does that mean?
It means it handles the messy, complex, and unpredictable compositions that you find in a typical shredded ELV scrap stream, both today's and future streams, without sacrificing performance.
The genius is that this process is economically viable because it dispenses with the immediate need for the most expensive part of the whole process, that absolute perfect high-cost LiBS sorting.
Exactly. It uses existing industrial melting infrastructure, which is a critical economic point for adoption. You don't need billions in new capital expenditure. You just need to change the alchemy, the process after melting, to transform the low-grade input into a high-grade output.
Okay, let's talk about the metallurgical magic. They achieved this superior performance using advanced principles related to heterostructures and accelerated precipitation. This sounds like pure science fiction, so let's use the food analogy to break it down.
Perfect. Think of primary aluminum production as slow cooking a complex gourmet meal from scratch. It takes immense energy and time, and you use only the purest ingredients. Downcycling, as we know, is turning that gourmet meal into slop because all the ingredients got mixed up.
So what is this new upcycle method? Is this the instant gourmet meal?
It is. You are taking instant noodle ingredients, the cheap, mixed, impure scrap, and through very precise, very rapid changes in temperature and pressure, you force those alloying elements to behave exactly the way you want them to. That is accelerated precipitation.
Okay, what does accelerated precipitation actually force the elements to do?
It manipulates the solidification rate. So usually when impure aluminum cools slowly, Those tramp elements like iron form those large, brittle intermetallic shards we talked about,
The glass shards.
the microscopic glass shards. Accelerated precipitation forces those elements to precipitate out rapidly as microscopic structures, the heterostructures.
So instead of forming large, dangerous shards, they form tiny, beneficial internal speed bumps. Is that right?
That's a wonderful way to put it. These heterostructures are nanoscale particles or secondary phases that are deliberately dispersed all throughout the alloy. Their job is to block the movement of dislocations.
What are dislocations?
They're just defects in the crystal structure that allow the metal to yield and ultimately fail. So by organizing the chaos into these internal speed bumps, you significantly increase the metal's strength and hardness. You completely compensate for the messy chemical input.
That is genuinely incredible. They're using the impurities not just as some inert filler, but as functional structural components through advanced manipulation of the cooling process.
And the result is dramatic. It's why this is such a landmark discovery. This upcycled alloy achieves yield strengths more than double those produced by previous rapid solidification methods.
Yeah.
Double the yield strength. This isn't just good enough recycled metal. This is superior material, designed for the reality of the recycling stream.
Precisely. And most significantly, it surpasses the commercial automotive alloy spectrum.
It's better than what's out there now.
It establishes a new circular low-emissions path to recover high-value aluminum that performs better than the high-purity, primary metal-dependent structural alloys we rely on today. This fundamentally redefines scrap aluminum from a waste problem to a premium, high-performance material input.
It takes the pressure off the need for perfect sourcing and allows manufacturers to leverage that massive 95% energy saving without compromising the safety or the structural integrity of their vehicle design. This is a game changer for supply chain sustainability. This entire discovery, it fundamentally shifts our strategic view of aluminum scrap.
Completely.
It goes from a waste liability, the villain we talked about, to a guaranteed premium raw material and really a hero that's critical for our high-performance future.
And this leads us to the long-term trajectory for materials science. The future isn't just about this one new alloy. It's about designing entire families of composition-tolerant materials.
Okay.
These are sometimes called uni-alloys or broadband alloys.
So instead of fighting the contamination forever, we're designing materials that just incorporate the contamination without a structural penalty.
We are building a metallurgical moat around the impurity problem.
That's a great way to put it.
These structural alloys are deliberately formulated to absorb the inevitable trace elements found in scrap without compromising the required yield strength or ductility. It means that future cars, when they get shredded, will seamlessly feed back into the system without requiring multi-million-dollar segregation steps.
Because the metal is engineered to accept the mess from the start.
It's designed for circularity.
That's incredible foresight. The global market is obviously responding to this competitive and regulatory pressure. Where is this technology and demand manifesting most rapidly today?
Currently, the Asia-Pacific region leads the global aluminum recycling market. This is largely driven by its enormous, rapidly expanding automotive industry and proactive government policies promoting resource efficiency. They're seeing the future demand very clearly.
And what about North America and Europe?
They follow, benefiting from their already mature, albeit aging recycling infrastructures and stringent environmental regulations that push OEMs toward recycled content. However, the adoption of advanced sorting, like LiBS and the optical sorting techniques, and this new upcycling metallurgy, these are critical areas for investment in these regions to close the gap.
And the demand is only going up.
It's going to surge exponentially. As automakers continue to increase the aluminum content in EVs for lightweighting, the demand for this now upcycled material is going to make that investment extremely lucrative.
This brings us back to something you mentioned earlier, the importance of a comprehensive material stewardship perspective.
Right.
You used the term life cycle assessment, or LCA, and the concepts of cradle to gate versus cradle to grave. We should probably clarify those terms for everyone.
Absolutely. So the simple cradle to gate view is just, how clean is the product when it leaves the factory? Using recycled aluminum makes that number look great because of the 95% energy save. But true stewardship requires the cradle-to-grave view. That means tracking the material's impact through its entire life, including its disposal.
So you have to look past the sale of the new car and focus on what happens when that car is inevitably retired.
Precisely. There's a key LCA methodology, the net scrap substitution approach, and it emphasizes that the full environmental benefit is only realized if we optimize product recovery and ensure material recyclability at the end of life.
Uh-huh.
If we create a component, but then we can't recover the material at a high quality, we've failed the long-term sustainability test. Maximizing ELV recycling mitigates that massive loss of embedded energy we quantified at the beginning of this dive. It preserves the resource perpetually.
It's the ultimate long-term investment. By solving the downcycling problem and creating materials that are stronger because they incorporate scrap, we are ensuring this vital metal remains available for our children's generations without the brutal energy cost of primary production.
It's closing the loop entirely. It's transforming the concept of waste into the concept of a reusable premium resource bank.
And that brings us back to the power of this specific discovery. If the environmental footprint of aluminum production can be reduced by 94% through recycling, and scientists can now take the messiest, most contaminated car scrap and turn it into a high-performance alloy that is stronger than anything currently on the market, it raises a huge, provocative question. What other common waste streams, plastics, construction debris, electronics, are we currently downcycling, just throwing away immense value, simply because we haven't applied the right instant gourmet metallurgy or material science alchemy to them yet?
It suggests that the future of resource scarcity will be solved not by finding new mines, but by mastering the science of what we currently consider trash. The material science of waste is perhaps the single most defining technological frontier of our time.